The biggest shift here is that AI systems are learning to adapt with far less hand-holding, from extracting structure out of pure noise, to tuning themselves at test time, to learning vision from temporal change instead of heavy augmentations. That matters because the bottleneck is no longer just model size, it's how much prior structure we force into the learning loop. Across these results, the message is clear. Weaker assumptions are starting to win. Keep watching, because the details show where that principle works, where it breaks, and what it means for building the next generation of models. Let's explore the first paper, Semi-Supervised Noise Adaptation Transferring Knowledge from Noise Domain. Semi-supervised noise adaptation. Transferring knowledge from noise domain introduces a setting where a synthetic noise domain generated from random distributions such as Gaussian noise is used as a surrogate source domain for target classification when only a few target labels are available. The core idea is that noise need not be semantically meaningful to help learning. If noise classes are assigned a one-to-one mapping to target class indices, then training a shared classifier on both domains can induce a discriminative class structure in the noise space and transfer that structure to the target space. The paper proves a generalization bound for SSNA and turns it into the noise adaptation framework, which jointly minimizes labeled target risk, noise risk, and a distribution alignment term in a shared representation space. Its preferred alignment objective is negative domain similarity. On CFAR 1.0 with ResNet 1.8, NAF reaches 67.9% accuracy versus 55.55% for ERM, a 12.35 percentage point gain, and on CFAR 1.0.0, it improves from 41.43% to 49.04%. It also scales to fine-grained recognition, reaching 50.86% on CUB, 2.0.0, 86.58% on Oxford Flowers, 1.0.2, and Femotradive, 7% on Stanford CARS 800 all sexo halfems, while ImageNet 1K improves from 36.11% to 37.1%. The method plugs into SSL systems like UDA and FixMatch, adding up to 20.99 points on CFAR, 1.0 at Epoch 20 for UDA plus NAF. Ablations show that both noise risk and alignment matter, that cosine-based alignment beats Euclidean distance, and that removing the class discriminative structure of noise collapses performance, confirming that the transferable signal comes from structured noise rather than semantics. Let's explore the second paper, UTTT towards generalizable PET image denoising via test time training. UTTT, developed by researchers at Beihang University, Tsinghua University, and ByteDance, is a 3D PET denoising framework that tackles the core failure mode of fixed parameter models under scanner and dose distribution shift by embedding test time training directly into a U-shaped network. The method replaces standard attention with two differentiable adaptation blocks, STTT for spatial structural correction and FTTT for frequency domain noise suppression, each performing online self-supervised reconstruction updates during inference, so the model adapts to each test volume before predicting the restored full-dose PET image. On a base dataset with DRF equals 2, 3, 6, and 12, UTTT reaches 51.63 decibels, 50.01 decibels, 48.02 decibels, and 45.96 decibels, PSNR with 0.9823, 0.9741, 0.9621, and 0.9498 SSIM, while reducing lesion error to 0.1486 on average and staying lightweight at 10, 20M parameters and 43.52 G-flops. Against 5 PET denoising baselines, it improves average PSNR by 0.8 decibels over the strongest competitor on in-distribution data, and also generalizes best on out-of-distribution tests, reaching 46.86 decibels on unseen dose settings and 43.1 decibels on unseen scanners. Ablations show that combining STTT and FTTT is necessary, and the proposed gated inner model outperforms linear and MLP alternatives, confirming that dual-domain test time adaptation is the key contribution. Let's explore the third paper, You Don't Need Strong Assumptions Visual Representation Learning via Temporal Differences. In You Don't Need Strong Assumptions, Visual Representation Learning via Temporal Differences, Nina Dithanker, Alexei Gladstone, Jan LeCun, and Hengji argue that modern vision pre-training still depends too heavily on augmentations, masking, and cropping. And they introduced temporal difference in vision, or TDV, a self-supervised video method that instead uses a causal next frame constraint. TDV trains a frame encoder and a motion encoder, so the current frame embedding plus an encoded RGB difference predicts the next frame embedding, with an EMA teacher and a Dino-style collapse prevention loss. The paper's key empirical claim is that weaker assumptions become better as scale grows. On ImageNet, 1K subsets from 0.1% to 100%, the preferred masking ratio shifts from 50% toward 30% and then 10%, indicating that stronger inductive bias becomes a bottleneck at larger data scales. Pre-trained on something v2 for 20 epochs, TDV reaches ImageNet KNN top 5 of 17.05 on ViTB, matches or slightly trails Dino and iBot on ADE20K and Cityscape segmentation, and is stronger on motion-centric tasks, cutting MPI Cintel optical flow error to 10.97 clean and 11.85 final on ViTB, while also improving scene flow bad pixel rates to 54.62 at 0.5 px and 37.33 at px. Ablations show the method depends critically on both the motion encoder and the MSE temporal prediction loss, since removing either causes collapse. That's a wrap on today's AI paper highlights. Thanks for watching.